Good morning, everyone. I'm going to go through, I guess, a day 2 on related rates. We didn't, we had a good day, but we need to look at some more. And it's okay. I guess I'm pretty much doing the whole assignment, but that's okay. These are still very important problems. I'm sure I'll just tell you this: when the test comes on this chapter, and we're getting pretty close to it, I will have this on the test. All right. So I got one request, and I think we were looking at 17 when the class period ended. So I just want to continue this a little bit. So let's see, I got to go back for context here. Number 17. So yeah, we've got a sand and gravel plant. Sand is falling off a conveyor, and it makes a cone, a conical pile, and it's falling off this conveyor at the rate of 10 cubic feet per minute. So yeah, this is one that I didn't have, so let me just copy this. We'll bring it over. So we can at least see now. So we've got this cone, and which is natural. The diameter of the base of the cone is approximately 3 times the altitude. So that's, you notice in my drawing here, I've got a cone, and I've got the height h marked, and then they said that the diameter of the base is 3 times the height. So I wrote that as 3h there. All right. At what rate is the height of the pile changing when the pile is 15 feet high? So you notice I wrote up here in the top corner, h equals 15. Let me explain to you where I got this r from. R equals 3/2 h. Well, the diameter of the base is 3 heights, 3h. The radius is half of that. So if you just take 3h divided by 2, you're going to get this 3/2 h. Okay, so that's where I got that from. They're asking at what rate is the height of the pile changing. So notice I wrote down dh dt. That's the unknown. And we were told the volume is changing at 10 cubic feet per minute, so we know dV dt. And then they gave us the formula for the volume of a cone. Okay, so we're pretty much ready to dig in. So the first thing I did is I wrote the volume of a cone. I took this formula, V equals 1/3 pi r squared h. And I at least reduced one of the variables here, because they told us that the radius and the height were related. I am making this substitution. In place of r, I'm plugging in 3/2 h. So you notice how r squared is now 3/2 h squared. Okay, so here's what happens when you square that. You get 9/4 h squared, and h squared times h is h cubed. So here we finally have, I guess we can put that together even further, can't we? We can take the 1/3 and the 3/4 and put them together. That's not 1/3 times 9/4 is 9/12, which simplifies to 3/4. So finally, here it is. The volume of this thing, based on the height, is 3/4 pi h cubed. Now it's time to do our implicit differentiation of the whole thing. So on the left, we have dv dt. Okay, 3/4 and pi, those are both constants, so nothing's going to change when we do a derivative. H cubed, bring the 3 down, 3h squared, and then dh dt, chain rule. So I just simplified a little bit. 3/4 times 3 is 9/4. So there, that's about as simple as I can get it. And now you make your substitutions. In place of dv dt, you plug in the 10 that was given at the top. And the only thing missing in this whole thing, oh, h is given, right? H is 15, way up there in the top right. So I took 15 squared. The only thing that's missing is dh dt. So we can solve for it. You know, we just will divide both sides by 9/4 pi times 225. And there it is. The rate at which the height is changing. And we always like to leave pi in our answers. I should have probably put down feet per minute. We'll write that on there now. Yeah, you should label your answers in these. So that's number 17. Any questions on that one? Comments? Okay, let's go to number 18. And I think we started this one yesterday, didn't we? Anyway, yeah, we did. We got right up to the point where we were going to do the implicit differentiation. But let me just review. Okay, 18. Again, I don't have the problem in front of me. Let's go get that. Number 18. So here we go. So 18, a conical tank with vertex down. So this is, the cone is upside down, like I've made it in the picture there, is 10 feet across the top and 12 feet deep. So kind of small, but you can see I made this drawing here, 10 feet across, 12 feet for the height. Okay. Water is flowing into the tank at the rate of 10 cubic feet per minute. So that means that that's the rate of change of the volume. So that's this dv dt up here in the corner. Find the rate of change of the depth, the height. So there's my unknown, dh dt, when the water is 8 feet deep. So at this particular time, h equals 8. So I'll explain to you where I got the r from. I've done that already, but if you go to the bottom, I made an enlarged picture here. The diameter of the tank is 10, so therefore the radius is 5, which I show here. The height is 12. So one thing is certain, that ratio of 5 to 12 for radius to height will remain constant. I mean, the ratio will stay the same. So I just wrote that relationship down there. The radius is 5/12 of the height. So anyway, then I use this proportion, 5 is to 12, as what is to 8, because 8 was the actual depth of the water at the time we're supposed to figure it out. And I came up with 40 equals 12. You know, you wind up with 10/3 or 3. Yeah, so the radius is 10/3. Okay? All right. So when I relate the variables, we already know the volume. Whoop, the volume is 10/3. The volume is 1/3 pi r squared height, pi r squared times h. So again, we have an r and an h. We have too many variables, but we have this relationship. R equals 5/12 h. So in place of r, I plugged in 5/12 h. So r squared is 5/12 h squared. Now, on to the next page. Yeah, so here's where we pick it up. V equals 1/3 5/12 h squared times h. And then I squared that, I put it all together, and now I have just a V equals something something h formula. I mean, here we are, right here. I wrote it this way is even better over here on the right. 25 over 432 times pi h cubed. So we got the constant in parentheses just to make it really clear. It's time now to do the differentiation, the implicit differentiation. So dv dt equals, and now we do the power rule, 3 times this constant. Well, that's 3 times the 25 on the top. Reduce the power by 1. The pi, that's all constant. Reduce the power by 1, and then don't forget, use the chain rule, dH dt. So now it's time to start plugging in what we know. I don't have that all on the screen, but h was 8. The height of the water was 8, so I plugged in h equals 8. And the volume change is 10, leaving the only thing we don't know, dH dt. Carrying out the calculation one step further, but leaving pi as it is. And then after a bunch of horsing around, just simplifying things, I got it down to 9 over 10 pi. Any comments? Any questions? Okay, I'm going to get this out of the way. All right, then we will move to number 21. Yeah, so this problem, I copied the picture, and we've got these things that are given. I guess, again, let me go get the text. All right, just take a second. Number 21. Moving ladder. So I think I'm just doing the part A here. You guys can finish this up. Copy the image. Okay, here we go with 21. A ladder 25 feet long is leaning against the wall of a house and it says see the picture, and we've got the picture right there. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. Not a good thing to hear about if you were up on the ladder, right? You wouldn't want to have that bottom of the ladder sliding out. But anyway, that is sliding out at a rate of 2 feet per second. Woo, that's pretty quick. That would be time to get off the ladder if you were up there. All right. How fast is the top of the ladder moving down the wall when the base is 7 feet? And we'll just do that one. There are 3 parts to it. When it's 7 feet, when it's 15 feet, when it's 24 feet. Okay. Wow, when it's 24 feet, the ladder is almost smashed. You know, it's only a foot from the ground. Okay. So I drew this picture. I drew it backwards, but basically we've got hypotenuse is what the ladder is, 25 feet. You've got this distance, horizontal distance, x, and I could have called it y, but I called it the height, h. How high is the ladder off the ground? X is given to be 7. The height, how fast the height is decreasing, that's what we're supposed to find. dH dt, and how far it's horizontally being pulled out, that has a rate of 2 feet per second. So there's our given information. This time it's a right triangle, so guess what? The relationship is the good old Pythagorean theorem. If we take the height and take h squared plus x squared, we should get 25 squared, which is 625. Right? So I did this. I solved it for h, and because that's what h is the guy we're trying to find out about. So h squared equals 625 minus x squared. And then h equals the square root of 625 minus x squared, which I wrote as being to the 1/2 power. All set up for now for differentiation. So we take the derivative of both sides, dH dt, and then we do the power rule, 1/2 times 625 minus x squared to the negative 1/2. Chain rule, negative 2x. Chain rule again, dx dt. Because we're differentiating with respect to time, and x is foreign to that, so we have to do the chain rule. All right, so I wrote that in root form. There's 625 minus x squared to the negative 1/2 is a square root on the bottom. The 1/2 and the negative 2 cancel into, and you just have that negative x left. Now substitute the h dt we don't know. We do know x is 7 and dx dt is 2. And there it is. And I should have labeled this again. It's feet per second. So the reason it's negative, if you're wondering, and you should, that it's negative because the height is going down. It's decreasing. So it's the height of the ladder is decreasing at about what? Just a little bit over 1/2 foot per second. So remember, the horizontal movement, that was 2 feet per second. The ladder coming down the wall is going down at a little bit over 1/2 foot a second. Okay. Comments or questions? All right. So that's number 18. That was number what? 21. Yeah. So let's go to 25. So I've got the problem off here to the right. So it's an air traffic control situation. An air traffic controller spots two planes at the same altitude converging on a point, obviously a red flag. As a traffic controller, the last thing you ever want to have happen is a midair collision. But the two planes are heading at each other at right angles. The picture shows this. One is coming, from, it's heading downward, and this one is heading to the west. And they are set to converge right at that point there at the vertex. All right. They're flying at right angles to each other. One plane is 225 miles from the starting point. That would be this one down here. And he's traveling at 450 miles per hour. The other plane is 300 miles away, and he's going 600 miles per hour. At what rate is the distance between the planes decreasing? And then the important follow-up for the air traffic controller is how much time does the air traffic controller have to get one of the planes on a different flight path? Yeah. So that's the problem. So now let's take a look at this. So the only thing I added to the figure is I called this horizontal distance x, this vertical distance y, which made sense. And then the distance between them, the book has already called S. I don't know if you can see that there. It's an S. Okay. So how are those related? Well, they're related using the Pythagorean theorem. So I wrote up, I mean, really, it's another version of it is x squared plus y squared equals s squared. And then if you take the square root, you get s equals, okay. And then given the x plane, his distance is 225, and his speed is negative 450. Let me just take a look at the problem one more time. Yeah, the reason it's negative is because he is moving to the left. Got it? So that's just, for me, that's just indicating to me he's heading in a negative direction. Likewise, the plane that's going y is 300 miles away, and he's going 600, and he's going downward, so his is also negative. All right. We are supposed to find how fast is s decreasing. Find ds dt. All right, so we've got the problem set up. So this equation up here, s equals the square root of x squared plus y squared, can be written this way. S equals x squared plus y squared to the 1/2 power. We're set. Take the derivative. ds dt equals power rule 1/2 times x squared plus y squared to the negative 1/2. Chain rule 2x. Don't forget dx dt plus 2y dy dt. And that's all being multiplied. That's why I put that in brackets. One of the common errors students make is they will write this times right here, like I have. That, I don't know if you can see my pointer right there. Nah, never mind. I didn't know how to do that. Let's get rid of that. Pointed at the wrong thing. Okay, anyway, that little multiplication symbol, and then they won't put the brackets, so they won't, they'll forget about that. This plus is part of the multiplication, and if you don't have the parentheses there, you'll get an error. Okay, so now, I mean, the one good thing about related rates is Well, all I did was rewrite the square root, but you don't really have to simplify this any further. You don't have to get this numerator over there and see if you can cancel. You could, by the way, cancel 2's, but I mean, you can get to your substitution. So I plugged in all the givens. X, X, Y, dx dt, and dy dt are all up here at the top. You plug them in the appropriate spot, and you wind up with a negative 750 miles per hour. Okay, so that's how fast, that's pretty quick. These planes are approaching each other at 750 miles per hour, and it's decreasing. That's why it's negative. And if you figure out the part B, he's got a half hour. So anyway, that's number 25. Comments, questions? The last one we're going to take a look at is number 27. So here we've got this thing all set up for us here. So, sports, baseball, a baseball diamond. I know we all call a baseball diamond a diamond, but it's a square. These are all right angles, Okay, so it has the shape of a square, and the sides in baseball are 90 feet. So the baseline, 90 feet between all the bases. A player running from second to third base at a speed of 25 feet per second is 20 feet from third base at the moment. At what rate is the player's distance S from home plate changing? So here's my drawing to wrap that up. So here's the baseball diamond. The scale is wrong, but that's okay. This here's the position, that big dot there. That's the position of the player at the current time. He's 20 feet. That's supposed to be a foot mark. It's not a double. It's 20 feet from third base. And then of course, we've got the 90-foot distance to home, and S is the actual distance he is from home plate at the moment. So here's the picture we need. So X, actually it's not a variable, it's a constant, 90. I mean, he's not going to get, in our problem, he never gets past third base. So 90 is just going to stay there. His distance Y, I'm calling, is 20. And his rate of speed, dy dt, is decreasing at a rate of 25. And what is that, feet per second? Yeah. Do I have that right? Yeah. So let me write that label in there. 25 feet per second. Okay. So now we're ready to do the problem. The all-important setup is complete. So, the equation, the Pythagorean theorem, s squared equals y squared plus 90 plus 90. And again, that's not a variable, that's a constant. So then if we take the square root of both sides, here's our formula, which we can write as on the right here, y squared plus 90 to the 1/2 power. Differentiate, and we have ds dt equals, do the power rule, 1/2 y 90 squared plus y squared plus 90 squared to the negative 1/2. Chain rule, 2y. Chain rule again, dy dt. Then putting that 90 squared, I multiplied out. That's 8,100. And that's the square root on the bottom. So I stuck it on the bottom. The 2 cancels with the 2 on the 2y. And so basically, there it is, y over the square root of y squared plus 8,100. And when you crank it out, oh, well, we got to substitute. What's y? Y is 20, so we plug that in, and dy dt is negative 25. So you plug those in, and he is approaching y squared. I'm not sure what you're asking, but there was a y squared under the square root. Y was 20, and 20 times 20 is 400. So that's the reason. That's where I got the 400. I was just checking out a message that I just got. All right. So anyway, when you plug that in, he is approaching home plate, the actual home plate, at 5.4 feet per second. It's negative because it is decreasing. As he runs, he's getting closer to home plate, and his distance is decreasing. Did I answer your question, whoever asked about the y squared? Please speak up. I mean, speech works so wonderfully well. And then we don't have this interpreting text and so forth. Did I answer your question? Oh, okay, I did. Good. All right. Does anyone else have a comment or a question on this number 27? So what we have there is 5 additional examples for you to think about, peruse. That's almost everything. I'd like you to finish it up, and we'll go on to a new lesson tomorrow. If not, that's we're going to call it quits today. Thank you. I appreciate your attention. I wish you guys would speak up more, but thank you.